All right, welcome everybody. Those of you who are here from the first talk still, welcome again. Our next speaker is Dr. Syed Uddin.
Not
doctor, sorry.
In 1 year.
But he will be. He's currently doing a PhD at Swinburne on cosmology. He's also a member of CAASTRO, who have given us a lot of support here, and I hope you enjoy his talk as well.
Thank you very much for introducing me. So my colleague just talked about the CMB, right? So you understood that CMB is something about the universe that.
Hang on, some of us are here for the first talk, so we don't know what CMB is.
No, I'll be talking about this one.
Yes.
Just making clear the contrast, because he talked about a tool that you can use to study the universe, and I will be talking about a different tool that also you can use to study the universe, and that is supernovae. So how many of you know the word supernova? I hope many. All right?
No.
Many?
No.
Okay, no problem. Since you know, you get a red ball.
No.
Okay, sorry. How many of you know the word dark energy?
No.
Ah, are you a scientist? Okay, you got one. You should be happy. Anyway, so in my talk, since there is a distribution of ages here, especially the kids, if you don't understand anything, just raise your hand. It should be very interactive talk. It's not like, I'm not going to talk in details. So what I'm going to do is just tell you the story of the universe.
What's the universe? You'll have to...
Yeah, so universe is something that I cannot define. So this is, the universe is something that we live on,
Right.
and we can observe its property. But I cannot say like what is the real universe is, because we can observe a certain part of the universe.
Yes.
And and beyond that there are beyond the observable universe there is many things. So these are the highly philosophical questions. So let me just talk about the facts now in 10 minutes, and then we can go to the interaction. So supernova help to discover a lot of things about the universe. So as one lady in the back told, dark energy. So before going all to that, let's just take a step back and just think what we really see in the night sky. So if you go outside as an ordinary person, not as an astronomer, what do we see? We see just some stars, right? So if I'm giving the talk 200 years ago, I will be telling you that this is our universe. Because at that time we knew that the stars that we see in the sky is our universe. But as you know, the telescope has been developed. We have observed the sky in details, and you know the word Hubble Space Telescope, right? Okay. So now I'm going to show you that what you saw with the Hubble Space Telescope. I will try to play a movie. So just to give you an idea what I'm meaning. How you play movie here,
I think you
just click. Oh yes. All right. So this is the stars that you see. Now you're zooming in a blank part of the sky that Hubble Space Telescope took photos 10 days at a time, right? And you see the blank space. But you see this one is coming out, lot of galaxies, okay? So that I wanted to tell you that in 200 years, we developed our technologies in so much great that we are discovering these galaxies that were created just less than 1 billion years, the age of the universe. So our universe has an age of almost 14 billion years, roughly. To be correct, it is 13.7. So we are now looking at the galaxies that are less than 1 billion years. This is just to give you a contrast that what we are observing at this moment as a cosmologist. All right, so next, before I go to the supernova cosmology or the dark energy, we already discovered the universe expanding, right? So we can just spend one slide to learn how this happened. Okay, because it just didn't happen suddenly that universe, someone says. So what happened? Albert Einstein is a famous face, right? So he had this relativity, And he said that he has an equation that describes the universe. The universe is homogeneous and something. Then two other people, Alexander Friedman from Russia and George Lemaitre from Belgium, they both solved Einstein equation and found that universe should be expanding. But at that time, we knew the fixed stars is our universe. So so that is a contradiction. So what happened? People actually didn't know that what would be the right or wrong. Is the equation is wrong or right? Then this is the equation that they gave. Don't worry about the equation because we are not doing any math here. Just to give you this H is the term that says the universe should be expanding. Because this is a very big statement. From static universe, you are suddenly getting an expanding universe. And then this guy, Vesto Slipher and Edwin Hubble, they both jointly worked together and they found the universe is expanding. And this is the graph that shows that if a galaxy is far away, its velocity is also that much greater. So you have a linear relationship between a distance of the galaxy and its velocity. And this is the first proof that the universe is expanding. Okay? And to measure the distance of these galaxies, we needed a certain type of stars called the Cepheid variable. Otherwise, this would not have been possible. And the lady, we got her face cut. But anyway, her name is Henrietta Leavitt Swan. And she was the person who discovered this special type of stars that helped to discover the universe is expanding. Anyway, so that's done. Now, I get a lot of questions actually, how the universe is expanding. If they're expanding, is the galaxy expanding? Are we expanding? No, this is not the case. Think of the space like a bread. Okay, you think of space like a bread. Even though space it doesn't have any shape, right? Or we cannot see it. And all the galaxies are the points on the resin. So if the bread is growing, what happens to the resin? The distance between them is also increasing, right? So that is what actually happening with our universe. So the space between the galaxies are moving, and so everything is moving about. And that's actually by the expansion that we mean. And now we come back to supernovae that I am supposed to tell you about. So what are supernovae? So I have a galaxy and I have a graph-like thing, right? So now you will see this yellow point on the graph that will move. Okay, I will play it again, and you will see a star will pop up on the left-hand side. At the same time, the yellow point will grow, and that is a supernovae. So supernova is a star that is a dead star. So it ends its life with a flash. So let's see how it works. It will be a slow, quick movie. Yes, you see, a star pops up, and the light and that white ball, the yellow ball that went up and down. If you see it again, did you see everyone? So if an object in the sky behaves like this is a supernovae, because a lot of transient object is there, right? You see meteor going on, you see a lot of different things. So what is a supernovae? Because supernovae is something that flashes and goes back. It goes back means it comes down, it gets fainter. So this is a typical signature of supernovae. So if someone asks you what is supernovae, you can just draw this curve. This is a supernovae, right? You can tell everyone. And in terms of physics, what is really happening? So if a star is massive, from the gas, the stars can have two phases. One, it goes to the upper hand, and ends up as a white dwarf. If it is a large star or massive star, then it becomes a supernovae, like in the bottom. Okay, so we don't need to talk about the details. Just look at what is happening between two types of stars. Small star, no supernovae. A large star, it has to go through a supernovae. And next, so why supernova is important in cosmology? Because we are thinking of it as a standard candle. It is like you have a 10 watt or 100 watt bulb in the space that is shining constantly, right? So if you all, especially the kids, do you see the graphs here? Like there are a lot of graphs, right? So if I say that they correspond to one standard thing, do you all agree?
Yes.
No.
That's what.
You will not agree because the curve has different, there are many curves and they are scattered, right? Like one is close to 18, one is close to 20, right? So that they don't agree. So to make them standard, we have to make a one single curve, right? And that people have done in the in the end of 20th century. They found a way to match all the light curves to make a one. And that means now you can use supernovae as a standard object. And how it works? So imagine you have two lights, okay? Both are 1000 watt, and you will be moving one away. So what do you expect when you're moving away? It gets fainter, right? And so then you will be able to determine its distance. So how it works, let me show you a video. So you will see that light in the right, the bulb in the right goes away, and its wattage is also decreasing, right? So the more distance it covers, the more fainter it gets. And it's just inversely proportional, right? If you go far, it gets faint. So that's how, if you have a standard object, and if you are looking at in different places or in different distances, you can measure it through distance. This is how the supernova works. And in cosmology, what we do, we really measure the distances in the universe, and then we feed the models. This is the only way we tell that our universe has this much energy, this much dark matter, this much dark energy, and everything. All right, I do not want to show equations in this talk because it's a public talk, but these are our bread and butter. These are our tools. If I don't show them, that I don't give you my secret. So, little m. Think of the light that goes away, right, in the previous slide. If I could play it again. No, the right bulb that was going far. Think of it as a small m, and the big M is the light is the magnitude that it had when it was not moving. So that means this is true magnitude or true brightness, and small m is the brightness that you saw when it moved away. So how far it moved away gives you this d. So that's how you calculate distance in astronomy. Just one equation that gives everything. But if you remember the equation that I showed you, the expanding universe, the velocity and distance. So we got the distance, we need the velocity, right? How do you get the velocity? We have another information that we can take. We can look at the spectrum of objects.
What's velocity?
It's just how much you run speed, your speed, but in a particular direction.
Thank you.
Yeah. One thing I want you to notice here is that there are different lines, black lines, right? Can you see that in some cases, if you go from bottom to up, the black lines are moving, right? And you see that on the left, you can read nearby galaxy, distant galaxy, very distant galaxy. So that means the objects that are far away, the line moves towards the rarer side, right? And that's how we calculate its velocity or redshift. So we got everything, the distance and redshift. So we got the V's for the velocity, we get the velocity done. So basically, I am teaching you the basics in astronomy, how to get the distance, how to get the velocity. And if you get all this, you can just say the universe looks like this. All right, I talked about supernovae, but supernovas are very rare object. So in a typical galaxy, you have only one per century. So, but the good thing is that there are billions of galaxies in the universe, right? So there is a chance that you get, if you look at any time of the in the sky you will be looking at, you will be finding an supernovae. But the thing is that they are random. You don't know where it will pop up, right? So people, they designed a systematic search to find the galaxy, find the supernovae. So what we do, we put a pointed telescope in a certain part of the sky, and we keep taking the images, and we go back to the similar part again. We take the snap again and see the difference. If something pops up and matches the light curve that we saw, that is a supernovae. And this is a typical pictures. So in the small box is a part of the sky. We zoom in, you see the arrow defines you the galaxy that we're interested in some date. Say after 1 month, we come in the middle and we take a snap again, and we just subtract these two images. And what we find? A supernovae, a point. The galaxy is moved out. So that's how we find a supernovae. And then what happened? Scientists wanted to study how much matter we have in our universe, so that the universe will slow down one day, right? To its gravity. Everyone is familiar with this, right? If you move something up, it goes back. Why is that? Excellent. Of course. Which color you want? Is green fine? Green, okay? All right. Excellent. So gravity keeps us stick with the Earth. Now, if the universe is expanding, there will be a time that it will come back, right? Like this one. It should come back. Because if we want to jump in, we fall back. So think about the universe that is expanding, so at some point it should bounce back. That scientists wanted to measure with the supernovae. But what happened in 1998, ironically, they found that universe not slowing down, but is speeding up. So it's accelerating. And that's why the mysterious force is called dark energy, because we don't know what it is. You know about dark matter, right? The word dark signifies that we don't know anything about it. So that's why we call it dark, right? So now we have a universe that is accelerating, and we don't know why it is causing. And that's the biggest mystery that supernovae gave us. And just to finish with, I will give you a plot. So the thing is that physically I cannot show you, right, what is dark energy or what is universe, how. There is no physical evidence. The only evidence are data. So this data, you see a lot of lines, right? And they are very close to each other, right? So the point I want to draw here is that the difference between different models of the universe are so tiny, so our observation has to be very, very precise, very accurate. Otherwise, we cannot distinguish that what universe we are staying. So the supernova data gave us that our universe follows this green line on the top, and that is the universe with vacuum energy or the dark energy. It's the energy, we don't know what it is. That's why this is still a mystery, and that is the big question in cosmology. And my colleague showed this figure again, just to illustrate again. The dark energy is 73%. So the most of the energy of our universe is unknown. And we, as stars, or the visible objects, are only 0.4%. 23% is dark matter, the matter that we don't know, but we can detect that they exist. All right. These kinds of plots are very interesting in our area, because what happens, since we don't know the values very closely, we just try to match all the observations. Like my colleague talked about CMB, right? So there is a CMB line. SNE means supernovae. So measurement from supernovae, measurement from CMB, measurement from another probe called MBO. If I all collapse, I get a number that is close to -1, right? So this is the dark measurement of dark energy. If the dark energy exists, it should have some value. What is its value? So it is -1. You don't need to understand what is W. W is just called the equation of state. And also we want to try to measure if it is constant or not. At this moment it seems that the dark energy is constant. So everywhere you go, you see a constant dark energy. It's not diluting. Even the universe is expanding or accelerating, the dark energy is not diluting. So this is a very mysterious thing, right? That means if you expand the universe, something is created here. That's why it keeps it constant. Now the biggest problem is that you know the word quantum mechanics, right?
No,
I mean, just heard about quantum.
What does quantum mean?
Quantum means just, quantum actually a Latin or some word. I think it means how much, basically. So everything is quantized, that I can say 1, 2, 3. I cannot say in between. So this is like quantum. Like I should always say a discrete number or discrete values. That's the quantum theory, basically. I cannot say continuous thing. So when I say something 1, 2, 3, 4, 5, I cannot make a continuous line in quantum world. So quantum mechanics, they say
only certain values.
yes, yeah. You don't just want to be more specific, but anyway, there's a big disagreement, the energy that you see in quantum physics and the energy that we see as a dark energy. And the disagreement is 10 to the power 122. Now we live in the world which is highly developed, highly technical, but we still don't know why this disagreement holds. 122 times mismatch of the energy that we see in the universe and that the quantum mechanics predicts. And that drives us to study more. And I'm happy to share with you what Australians are doing, and I am personally also involved. And that's called the AUSJAS collaboration. So what we do, there's a telescope in Chile, it's called a Blanco. It has a big camera like this. This is the biggest camera in the world. That takes a picture of night sky and gives us image, right? And in Australia, we use this telescope. Does anyone know where this telescope, the biggest telescope in Australia? No, the optical, Parkes radio. No, it's in Siding Spring, Coonabarabran. So it's called the 3.9 meter AAT telescope. So we go there, we observe with a nice instrument called 2DF A omega. And this project will run for 5 years. We'll have at least 5,000 supernovae, and we will have a very precise measurement of the properties of dark energy. And this is our future goal, and with this I'd like to conclude, and I am happy to take questions.
That thing at the bottom, what is that? Is that etching into something, or is that a...
This one?
Yeah.
This is a robot. This is a surface, and there is a robot that configures a lot of prisms and optical like fibers, and they go directly to the spectrograph. And then we take a spectrum of so you can take spectra of 400 objects at the same time. This is a big development.
Was it a good question?
Oh yeah, of course. Any yes, sure. I forget. Yeah, there are a lot of other things actually. You can, when you have a break, you can just come here and take a souvenir. Yes.
With the principle of the universe continuously expanding at a fast rate,
Yeah.
how would that reflect on the planets that, for example, Earth or Mercury or Jupiter are slowly screwing themselves closer and closer into the
Yes.
gravitational field of our
Right.
Sun? And in regards to all our known galaxies,
Yeah.
are they also screwing themselves closer and closer together?
Oh,
Basically imploding on
that
themselves?
actually I should say a very good question, because the thing is that the expansion, to see the effect of expansion, we have to go of a larger size. So the planet or the solar system in general, they are in our neighborhood. They don't participate in the expansion. So to have the expansion, you have to go like a very long distance, like megaparsec. So it is, to answer your question, we have a group of galaxies, like our galaxy is Milky Way, right? And we can see Magellanic clouds, right? So we have to go a certain distance outside to see the expansion or the acceleration. It's not a local effect.
All our objects.
Yeah, that's right. So all system, a part of, so all of them form a gravity field, and they all are moving together. The systematic velocity, and we call it like a Hubble flow. So when you calculate this thing, we have to deduct this effect to see the overall expansion. So we want to subtract all the velocities of the local galaxies.
So the smaller, or the galaxies being smaller than the entire universe,
Yes.
they're basically contracting, whereas
Right.
in actual fact the whole thing's expanding.
Yes. Yeah.
Okay.
So the map that my colleague showed, that like you see the temperature fluctuations.
Yes.
So this you can think of like tiny clumps of galaxies together. You can think, but this is not the real case. But you can think of like that. So one spot is moving together, and another spot is moving together. It's like that. Yeah.
It's showing the same current.
Yep.
So folks, could I draw this to a close and give the speaker
Thank you.
one more question?
Sorry, Syed, there's one more question.
Oh yeah, sure.
How
Yes.
many galaxies are there?
So you know this word, you know this letter called like tilde, like this. There is a word. So I put a tilde before, and I say 100 billion. So it is approximate. It will be more or less. There is no exact number I can tell. So it's up, this thing, and then 100 billions. So to give you an analogy, we have so many galaxies. If you count them, they will be still larger than all the grain sand in all the shores in Earth. So if you count all the sand grains in Earth, so the number of galaxies will be more than that. Maybe you will count when you grow up.